Perfect. Hello, everybody. My name is Nathan Justin, and today I'll be talking about my work on learning optimal classification trees, robust distribution shifts, which is work done in collaboration with Sina Guy, Andres Gomez, and P. Vallanos. So what are classification trees? Well, classification trees are a branching set of tests based off the attributes of a given data set, which we call the training data set. Then after some series of tests, we assign a particular label to each sample. Classification trees in general are a very popular machine learning model, largely due to their interpretability, which is necessary in many problem domains like the social sciences. However, within these domains, machine learning models are susceptible to distribution shifts, which is when the training data and the testing data or deployment data are different. And so this can occur for many reasons. Sina in his last presentation gave one reason for it, and I'll give you perhaps another motivation as to why distribution shifts may occur. So say that you have a survey that you are trying to collect data for, and perhaps that survey asks very highly sensitive questions. And so the framing of the question, you can imagine, will determine the level of comfort an interviewee may have in answering that question to the interviewer. And so in your training phase, perhaps you have a question, I signify it with this beta here, that is maybe not framed in the correct way. And so perhaps in the deployment phase, in order to get better answers, you change the question slightly. However, what this may cause is a distribution shift to occur, because in your training set, you have perhaps a different distribution of questions than what you will actually see in your deployment phase. And this can cause a poor performance in that deployment phase, because if you're training on a model, you're training your model on the data that that doesn't look like your deployment data, then you may have much more errors than you would want. So in order to tackle this issue, we propose using robust optimization, which addresses this distribution shift problem without having to actually know what the exact distribution shift will be in your deployment phase. And it also has been shown to perform well, even if the distribution of your testing set is perhaps slightly different than what you anticipate. So with that in mind, we propose a robust optimization approach for building these robust classification trees. So mathematically, what is this problem? Well, this problem, we want to maximize the training accuracy, which is the number of correctly classified samples in the worst case distribution shift. So to break this down, we can, my figures are not showing up, which is great, but it's okay. So first you want to decide the tree structure. And so we can encode that into binary variables that relate to the branching set of tests and the labels that you assign. And you can also model the worst case distribution shift by a perturbation of your training set. And so this is through something called an uncertainty set in robust optimization. And here we model that by assigning a certain cost for perturbing a certain data sample as a certain feature. Then totaling the cost of total cost perturbation, we restrict that total cost by some budget. And this will model the allowable perturbations, which then allow us to model the allowable distribution shifts we may have. And then lastly, we want to count the number of correctly classified samples, but as anyone in the optimization space may know, looking at this is very nonlinear, discontinuous, which makes the formulation very hard to solve efficiently. However, we borrow a method from my co-authors on the paper Strong Optimal Classification Trees, where we transform the problem of counting correctly classified samples as a maximum flow problem. And then this gives us a linear objective and a linear set of constraints, and we're able to reformulate this problem and use an iterative algorithm to solve its optimality. So just to briefly go over the test results, so we took 12 different data sets and through different uncertainty sets and different tree depths, we derived a worst case test accuracy by perturbing our test data in many different ways. And the vertical axis here is the gain in worst case accuracy from using a robust tree versus versus a non-robust tree. And the horizontal axis controls the size of the uncertainty set, which controls the size of the number of distribution shifts you consider. And as you can see in general, with a tuned budget of uncertainty, we are able to perform better than a non-robust tree. And for each pair of plots, we also try to perturb our data in a way that was unexpected. And as we can see on the each pair of plots on the right, that we still have a favorable gain in accuracy, even with unanticipated distribution shifts. And so with that, thank you very much. We also have a paper, a workshop paper, and we're also working on a journal version. Thank you.